Okay, in this third lecture, I'm going to talk today about linear mixed effects and generalized linear mixed effects models. So these are quite mouthy titles. Now, the thing to watch for here is the word mixed. So mixed is only a small word in English, but this is a big word when it comes to statistics and econometric modeling. Okay, and essentially here, what happens is that the mixed bit is the difference between something that sounds like a good idea but is wrong and a professional standard analysis. Okay, so for the first time, what you've got here is a situation where just by following something that seems intuitive isn't necessarily going to avoid making quite dangerous mistakes. Okay, so these mixed effects models are quite simple. The difference between doing something that's intuitive and wrong and doing something that is of appropriate professional standard. It's also a sort of cousin of some of the things you've seen before. Okay, so linear mixed effects model is a sort of harder cousin of the linear model that you've seen before with the regression models, and similarly a generalized linear mixed model. This is a sort of harder version of the generalized linear models that we saw in the last lecture. Okay, but the mixed bit here is the thing that's different, and although mixed is a small English word, it's quite an important statistical word. So in terms of the problem motivation then, so these are all motivated here by a genuine industrial application here to the electricity industry. So the first lecture we're using regression models, linear models to correct for regional bias by estimating the average survey score for respondents from each region. And then in the second lecture we were using generalized linear models, here the logit and probit models, to estimate the probability that survey respondents give a high, low or medium rating. Okay, so we started with the first lecture on regression, the second lecture a slightly harder version of regression, probability regression. Now what you've got here is this problem. If you don't account for these mixed effects terms, it's why I say the term mixed, although it's a small English word, is an important statistical word here. So the problem you've got in both cases is that in neither case do the models fitted adequately account for correlations caused by the nature of the sampling frame. Now this sounds perhaps slightly pompous, but we'll show you what this means later in the lecture. There's some correlation caused by the fact you've got repeat measurements from the same hotel, so you have to think quite carefully here about how the sample is being constructed. Also, what is very important here is that if you just follow the intuitive approach in either the first lecture or the second lecture, that's not enough, and you can make a mistake. Include the mixed. Okay, so in this lecture, what we're going to add in is the mixed terms. So we'll speak therefore of linear mixed models and generalized linear mixed models. So the mixed term is an important statistical term. So it's a small term in English, small word in English, but an important word here. So the mixed term indicates correlation problems caused by the sampling structure. Okay, so this isn't just simply pure intellectualism. Okay, this is something that came out of a genuine industrial problem, as we've discussed before. What you have therefore is that these mixed models are a sort of harder version of the things you've seen before. So lots of the same basic interpretation of previous models remains, but in this case what you've got essentially is a professional standard analysis, precisely because you account for correlations caused by repeat observations and the nature of the data collection. Okay, so this is motivated, as I said before, by a practical industrial problem, and in this case what you should get is more precise estimates of the regional effect. So you start off with a practical industrial problem, and by using a harder model, in this case the mixed effects model, you can ultimately answer this industrial problem more precisely. Okay, so you've got essentially a harder version of what you've seen before, but much of the interpretation of the model and the calculations are essentially the same as you've seen before in the first two lectures. So what you've got here, the commands in R, in terms of how you're reading the data, and this is a lot of repetition from what we've seen last time. So the easiest way to do this is to usually save the data as a .text file, and when you do this, save it on a USB drive to make the file path shorter. The shorter the file path, the less likely this thing is to corrupt. Okay, that is the syntax when you use a Windows machine. and you need to make sure that you get the file path within the speech marks exactly correct. Once you've done this, the second row, third row, fourth row, and fifth row down, you've got scores. The first column scores the second column, scores the third column, scores the fourth column. That name there, scores, has to match exactly, precisely the name that you've called the thing in the first line with the read.table command. Okay, and sometimes people make mistakes with this, and then what we're doing here, the last 3 lines of code on the bottom of the slide, this is just the easiest way of using the vectorized nature of the R programming language to subset the data based on observations that have a regional affiliation of the survey respondent. Okay, so this is in some ways perhaps quite trivial, but at the same time not trivial, because you need a proper programming language in order to deal with a data set here of practical size. Okay, Microsoft Excel won't hack it in this instance. So the data structure here is actually relatively simple, but I think practically useful and a nice teaching example. And again, this does come from a practical industrial problem. It's not just something that was an academic curiosity. So one thing behind this is that we do have only one observation per survey respondent. Okay, but you do have repeat observations from each hotel product in the original data file, and it can be a little bit confusing when you first look at it. That product is the thing that needs to be accounted for these mixed effects models. Okay, so there is some correlation here if you're going to analyze this up to a professional standard, precisely because each respondent observes the same reality. So observations from the same hotel product, even if they come from different people, are correlated. Now what this leads to is a class of models that are variously called mixed effects models, linear mixed effects models, random effects models, panel data models, etc. And different people may call the same thing different names. Okay, so I come from statistics, I would call this a linear mixed effects model. If you come from economics, you might call it a panel data model. Okay, in R, the relevant terminology used is linear mixed effects model, which explains the reason for the commands used. So in order to do this analysis, then we for the first time have to use optional packages in R, but this is one of the best things about R, is that you've got this online community and various bits of packages and R code that are provided for free and for nothing by this online community of R users. So in this case, if you want to fit a linear mixed effects model in R, to do this you have to download the R package LME4, which stands for linear mixed effects. So the name of the package is LME4, so this just literally means linear mixed effects 4. So the point to emphasize here is that in R, much of the commands and the terminology has a statistical underpinning. You don't need to know that statistical underpinning, but it makes it easier when you're working with this thing if you just remember that often the commands and the names of things are deliberately named for statistical reasons. And then in R, in order to upload packages, in this case you would go packages, load packages, and then choose LME4, click OK, and it should do this relatively straightforwardly. So this is an optional package, it's not loaded automatically, but I think it's one of the common ones that are often loaded, so you've got a good chance that this one will work. If you are choosing a slightly more exotic R package, this might not work so easily. So if you are installing non-standard packages from CRAN, there are some things to help to do this. So in R, to see what packages are available for loading, just use packages, load packages. Now if the package that you want is not there, you have to download the required package from CRAN. Now CRAN is just the original website where you can download R from. It stands for Comprehensive R Archive Network. And then what you would need to do to install packages is if you go packages, install packages, and then you're asked to choose a CRAN mirror, and it's better to choose the UK, London or Bristol, or wherever you are in the world, so this will work better the closer you are to the physical location listed. For the UK this is London or Bristol, and one of them works better for my home computer. One of them works better for my work computer, so you might have to switch between the two. If you get one of these to work, once you've done that, you should be able to see a long list of packages that are available for download. And again, not just because I'm a Yorkshireman, this is really the best thing about this list of packages and code that is provided for free and for nothing from this user community. Okay, this stands in marked contrast to alternative statistical software that can sit behind a paywall. Now, there are some potential problems with the university computer network, but as far as I can tell, using R actually works better on the Bradford computer network than other institutions I've worked at. So on my work computer, standard packages actually loaded fine. On your personal computer, you should be able to update the list of packages via the R repository CRAN. And again, just to emphasize that this maintenance of packages and an active online community is probably the best thing about R and the best reason to use it, and probably the best way to use R is to get used to being able to teach yourself different things if you get stuck using Google and the various posts from the online community. Now, it's possible that packages may not update directly if you're using a PC on the university network. Now, this was once a problem when I worked at a different institution, and the work around this would then be to save the package code to a USB stick and then use the option packages, install packages from local files, and you can load the package from your USB drive. Now, when there isn't a global pandemic, the best thing to do would be to bring your laptop into class and see if you can get it working. Do email me if you've got problems with this. The earlier you email, the more likely I am to be able to help you. And on my laptop, I found loading R packages fine, but fiddlier than it should have been. Now, in terms of the layout of the rest of the lecture, so we're going to focus on two main problems really. First problem is the professional standard analysis of customer satisfaction scores and regional debiasing. And what we're going to do is use these linear mixed effects models to account for correlation caused by repeat measurements from the same product. Here the product is hotel. And then the second problem we're going to look at is professional standard estimation of the probability of high, low and medium scores. We're going to use a generalized linear mixed model to do this. And again, it's the same basic idea to account for correlation caused by repeat measurements from the same product, here hotel. Now note here that there is a certain jump conceptually. Okay, if you're doing this at a professional standard, you need to account for this correlation caused by repeat measurements from the same hotel. For the first time here, I think you see an example where if you forget to do this, you're still potentially following quite an intuitive approach using either a linear regression or a generalized linear model. Okay, but you're going to make mistakes if you don't account for this correlation that is naturally there in the sample. Okay, this is not just a purely academic thing, this is something that's intrinsically in the data and in an industrial problem. So analysis of this problem one then that we identified in the previous slide proceeds in 4 steps. So the first thing you need to do is to download the LME4 package. Okay, so if you're trying to do this in R and it's not working, this is the obvious first mistake that you might have made. Then how this works is that you start first of all with a model with no regional effect. You've just got some correlation caused by repeated measures. Then in step 3, one step beyond this, what you would do is fit a model with a regional effect and correlation caused by repeated measures. So it's important to emphasize here that even if there is no regional effect, there very definitely is some correlation caused by repeated measures that you need to account for. And then what you would need to do as a final step in step 4 is to use a chi-squared test to test for a regional effect and to try and test between the two models that are fitted in steps 2, step 3. Now, if the more complicated model in step 3 is significantly better than the simple model in step 2, then you've got definite evidence of a regional effect. However, if the more complicated model in step 3 isn't statistically significant in relation to the model in step 2, then there is in contrast no evidence of a regional effect.